The next session is the interstellar object session. And Gregg Cole's going to start us out. Gregg, sorry. And this is an invited talk. Thank you very much.
Hello, is sound okay for everyone in the back? Yeah, so I'm Gregg. I'm a PhD candidate at the University of Western Ontario in London, Canada, working under the supervision of Dr. Paul Wiegert. So I'd like to start off saying thank you to the organizers for the invitation. I'm really excited to share sort of the contents of what my dissertation will include, which is investigating dynamical pathways of interstellar transport. Now, when we talk about interstellar transport, this really emphasizes the idea that the galaxy is an interconnected sort of system of material. And star systems are not closed, but in fact, it shares material all throughout the galaxy. And this is sort of well thought of in terms of supernova. We've all probably heard the term, we are made of stardust, the very dramatic end of massive stars' lives. They spread the material out into the galaxy, and it gets incorporated into the next generation of stars, including the planetary systems. Now, when we talk about interstellar objects like 1I Oumuamua, discovered in 2017, 2I Borisov in 2019, and now 3I Atlas, discovered this year, these are larger macroscopic objects. And the interesting part about these is that they are the leftover remnants of planet formation. So they can contain more complex sort of molecules when being delivered from system to system, including things like water or organics, or maybe all the necessities of life being sent from system to system in the galaxy. Now, we have this subset of interstellar material that we've seen. These are these 3 interstellar objects, but it's not the only interstellar material that we have detected in the solar system. We've also seen interstellar dust detected by spacecraft. Now, the important thing to point out here is that the dust that we detect is different than sort of seeing these interstellar objects, because these are things that are sort of being sent from a system to another system. Maybe they get perturbed by interacting with a star, but for the most part, they're sort of being sent system to system. The dust, on the other hand, that we see is sort of being swept up by the solar system as it moves through the interstellar medium. So it's all the dust that we see sort of seems to be coming from one direction, and that's coming from the sort of apex of the direction that the solar system is moving. So we see the small things of dust, we see some large things, the interstellar objects. Now the missing link here is interstellar meteoroids. So for a long time, interstellar meteoroids were thought to be extremely abundant, and it's been a controversy for well over a century. And this is because the sort of indicating factor of something being interstellar in nature is its heliocentric velocity, and whether or not that's in excess to the escape velocity of the solar system at that location. So interstellar meteors, their speeds were estimated by eye originally. So as you can imagine, uncertainties were quite rough. And it was overestimated the number of sort of very fast meteors, and the interstellar population was dramatically overestimated. But with modern detectors implemented now, we realize that these things aren't so common. And in fact, we have yet to conclusively say with any sort of confidence that an interstellar meteor has been detected, despite some claims. So we have this sort of missing sort of region of interstellar material. So we see these large things down in, I'm not sure where the mouse is, there we go. This is the sort of the larger massed objects like the interstellar objects. We have some estimates for the flux of dust, but this line in between for all these intermediate masses are just extrapolated. Maybe they're constrained a little bit by non-detections, but a lot of it is unknown. And at all sizes, the sort of unknown thing too is their origin systems. Where are these things actually coming from? Because if we're able to actually determine the host system in which an interstellar object is arriving from, this gives us a very maximized scientific return, because we're able to investigate the systems in which they're coming from as a source of free sample delivery, just arriving right on our doorstep. So getting into what I've been doing, I've been looking into the idea that material is sort of arriving from a specific system and understanding what the characteristics of that material would have, and whether or not we'd be able to trace it back to that origin system. Rather than right now, when we see an interstellar object, we sort of do a dynamical trace back, but it's so uncertain. We're trying to put in so many stars and see which sort of system it comes by close at a relatively low speed. So the first paper that I published just earlier this year actually is a case study of looking at our nearest stellar neighbor Alpha Centauri system and seeing whether or not material can arrive from there. So what we did is we took Alpha Centauri and the Sun and we traced it back 100 million years in the galactic potential. And then we allowed it to progress forward, ejecting material and seeing whether or not any of that material made its way through the solar system. We only did 100 million years because anything beyond that, you're getting a very rough estimate of what the actual trajectory is because there's a lot of unknowns in the galactic potential. But we do a fairly simple model of the galaxy. It's just an overall gravitational potential from the bulge disk and the halo components. And you can neglect the individual forces of the stars because it takes a very long time before an interaction with a star actually perturbs your trajectory. So when we ejected particles from Alpha Centauri, we used a binary star system ejection velocity distribution. And this is because this is a triple star system. Alpha Cent A and B are a binary pair in the center, and then Proxima Centauri orbits around the pair of those. So we ejected material for that 100 million years, and again, we just traced it through the galactic potential and saw if any material arrived. And what we got was yes, it was a fairly small sample set. It was only 0.03% of all the material, but we did get this influx of material as Alpha Centauri passed by the solar system. And with this, we saw the largest influx is when Alpha Centauri was closest. And in fact, it's closest in about 28,000 years from now. And that is when we saw the peak sort of delivery of this material. So now that we know, yes, material can make its way from Alpha Centauri, what does this material look like? And we can look first at what the radiant of these particles would be. So the radiant is just the relative velocity to the sun inverted to sort of see where on the sky these particles seem to be arriving from. So this is in a heliocentric RN declination. And you can see this small red star here. It's kind of hard to pick out. This is Alpha Centauri's effective radiant. So that's its relative velocity inverted to see where it'd be arriving from. And all these circular points here are particles from Alpha Centauri, and then also these ones in this large region here, and they're color-coded based off of when they're arriving into the solar system. So first thing you probably realize is that there's this sort of cluster around the effective radiant, and then this much larger cluster around Alpha Centauri's on-sky position, which is that black star there. So I will indicate why there is this difference, but first I also plotted some of the interstellar objects that we've seen. So at the time it was only Oumuamua and Borisov, and we don't expect those to be sort of arriving from Alpha Centauri. They're complete opposite sides. And then some candidate interstellar meteoroids that were detected, and we also see that those don't quite match up. So this purple region here is the solar system's size as viewed from Alpha Centauri. And as Alpha Centauri sort of passes by the solar system, its on-sky position changes and the solar system appears larger. And so this purple region is sort of how large it appears. And you can see that the particles that do arrive in the future when Alpha Centauri is closest are in this sort of larger region of when Alpha Centauri has this sort of larger target to hit. And I will point out here with the ejection time and velocity of these particles, we get this cluster from the most recent ejections that have very fast speeds. And this is why we see that sort of larger cluster, because as Alpha Centauri is moving towards us, it becomes a time where it moves from a radial velocity to almost entirely tangential. So then the particles that are ejected that can make it to the solar system need to be extremely fast to traverse that distance and actually arrive at the solar system. So these are very, very fast, upwards of 10 to almost 100 kilometers per second ejections, which is a very, very small sort of tail of the ejection speeds that we would expect, the majority of which actually arrived being ejected more like 2 kilometers per second, which is interesting because this is around the peak for planetary ejection speeds. So again, this sort of explains this double clustering effect. And we didn't have a very fine resolution of ejection times, but when we run supplement simulations, we found that if we ejected particles almost at every time step, that whole purple region gets sort of filled out as you expect. But so that is why we saw this sort of difference. So we see particles coming in. We expect where on the sky they'd be arriving from. But what is this heliocentric speed when they get pulled into the inner solar system? So it has a range anywhere from 44 to 111 kilometers per second if to be detected in Earth's atmosphere at 1 AU. So this is quite a large range, but the median value is about 53. So this is sort of well above the escape velocity of the solar system at Earth's distance. So if it was detected as a meteoroid, it should be very distinguishable from ones that are right on that sort of boundary of bound to the sun and unbound. Now, another interesting thing we can pull out of these simulations is the individual trajectories of each of the particles that did make its way to the solar system. And there's a great paper by Murray et al. In 2004 on interstellar dust sort of traversing the galactic potential and how large it needs to be to survive things like magnetic deflection on small grains, interstellar medium drag, as well as grain sputtering, so grains sort of hitting each other and destroying their mass. And when we use their equations along with these individual trajectories like travel time, relative travel distance to its origin star, and velocity, we find this is very relevant to very small particles. The sort of size that was necessary to survive was anywhere from 2 to 150 microns, the median of which 7 microns, so much smaller than things that we can actually even detect in Earth's atmosphere. So things like 100 microns and larger. So most of the material that did arrive, again, traveled for a very short amount of time, galactically speaking, about 10 million years or less. And relative, the mean was only about 7 parsecs relative to its host star, but more like 1.6 when you look at the median. So we have this idea of how many of these simulated particles are arriving and their characteristics, but what does this mean for an actual expected flux? So it's very hard to constrain how many small particles or even interstellar object-sized particles are being ejected currently from Alpha Centauri. So what we did was we did a solar system analog. How many new comets from the Oort cloud are we seeing come into the inner solar system? What fraction of those are ejected currently from an encounter with Jupiter? And we sort of just made this analog and it applied it to Alpha Centauri. And when we did this, we saw about 45 interstellar object size, so Oumuamua size, 100-meter or larger objects entering the Oort cloud every year. It takes about 20,000 years for them to actually cross the entire Oort cloud at an average distance. That would mean there's about 1 million currently within the entire solar system. So an extremely large value, you might think, but the observable fraction is very small. It's about 10 AU distance from the sun, about Saturn's distance is only about a trillionth of the entire solar system. So that would leave us at about a 1 in a million chance of actually observing one of these things from Alpha Centauri. And this increases by a factor of 10 at the peak in 28,000 years. Now, what about interstellar meteoroids? So if we look at sort of the minimum size that's currently detected by radar objects, about 100 microns, the best thing we can do is kind of do a mass equivalence for these larger objects and just put them into these 100 micron or larger sized objects. And when we take into account sort of the very tiny moving target of the Earth, we get maybe about 10 per year that might enter Earth's atmosphere. So it's not really about the number here. It's the fact that it is a number. It's not zero, which is super interesting. But we haven't obviously detected any interstellar meteors, and this is an extremely small number. And in comparison to solar system meteors hitting the Earth at about 7 trillion a year, this is about 1 in a trillion of meteors that you might expect could be from Alpha Centauri. So this would be like finding a needle in an Earth-sized haystack, perhaps. But interesting nonetheless that this could be possible. And I have a little bit of a summary of that paper here, just some interesting values. But the duration of sort of material being delivered was over about 10 million year period, starting about 3 million years in the past, going 7 million years into the future. But again, the interesting part here is material could be delivered from Alpha Centauri. And if it was, this would be a relatively short time period of the ejection from currently observed. So potentially able to be traced back to that origin system if observed. So the next step that we took is looking at some systems that could likely be delivering material currently, and this is nearby debris disk systems because they have these sort of large reservoirs of material that currently could be being ejected and might be detectable at the solar system. So this is a work in progress. We're hoping to finish it up in the coming weeks here, and then hopefully finish my dissertation as well. So what we did here is we just looked at there's a catalog, it's a catalog of circumstellar disks. It has a list of nearby disks with an infrared excess, so dust essentially around the star. We looked at ones that were close by, so up to about 20 parsecs, and we got about a sample size of 18. They're not all listed here, and some of the ones that are listed aren't the ones we used, but I'll explain the ones we did later. And we chose these again because they're nearby, they could be ejecting material currently, and that makes them very interesting because they could be, if observed material from the systems, they could be potentially traced back to that origin system. Now, how we estimated material from these debris disks is we again used that Murray et al. Paper. They have a great analytical sort of expression of how much material might be being ejected from these systems based off of their infrared excess and therefore an estimated age. And then we applied this to each of the systems based off of their infrared excess and sort of weighted each of the particles separately. And this is very interesting because also if we were to actually detect material from these systems, get an idea of maybe what the flux is, we could maybe perhaps help constrain parameters of the systems themselves and how much material they actually do eject compared to some of the models are. So again, if we look at some of those radiant values from each of the star systems, this time we just have the effective radiant of the stars in these circles and then a heat plot of all the particles that are arriving from it. We see that we plotted some of the interstellar objects, Oumuamua, Borisov, and now we also have Atlas here as well. And we also see that there is no sort of direct link with the interstellar objects that we do know currently, but you have to check because you never know. So again, we can look at sort of the ejection time and velocity of these particles that resulted in close approach, and this is like the overall sample of all the systems. And again, we see that the majority of which are sort of recent ejections and at the planetary sort of ejection velocities that you might expect. And I should point out that the ejection velocity distribution that we use this time is for a planetary sort of scale ejection, hoping that if there's a debris disk, maybe there's a planet there and ejecting these particles. Again, we can look at the individual trajectories of each of these particles and get an estimate for what the sizes need to be in order to survive. And this time we got anywhere from 6 microns to 24 millimeters were sort of the minimum. So anything larger than 24 millimeters is sort of certainly survivable. And it's in this range that there might be some perturbations that you'd have to take into account. But 95% of them were within 6 to 280 microns. Another thing that we can now pull out from each of these systems is sort of some of the key characteristics. So from each of the star systems, we have its effective radiant, so where you would expect this material to be arriving from. And then we have how much of the material does get delivered, so a transfer percentage. We get the arrival velocity at the solar system, and then if you pull that into the inner solar system at 1 AU, what's the heliocentric velocity? And then you can estimate the eccentricity based off of an orbit that has a perihelion at 1 AU. So that's a key characteristic there is for the eccentricity, this changes depending on what the perihelion distance is. So you do need to take that into account. And then what are the average radiants of the actual delivered particles, and what are these sizes that you might expect from these systems? So we hope this is sort of like a cheat sheet. If an interstellar object is discovered, maybe quickly go to this, or an interstellar meteor, quickly go to this, see if some of the characteristics match up with what you might expect from one of these nearby systems, and sort of rule out ones that you want to do a trace back and see what the encounter characteristics are and whether or not that is a likely system of the origin of this object. And we can also make some estimates now for what the population of interstellar objects is in the solar system. So I have 2 different colors here. So you have a T-crit of 3 and 10, and these are in millions of years, which isn't written down there. So this is based off of when you might expect sort of a giant planet to form and actually start ejecting material. Otherwise, you wouldn't have material being ejected. So this does change based off of what value you assume. But instead of trying to draw values out of this histogram, I circled the sort of current population, the total from these nearby debris disks for these 100-meter larger objects, and you get a couple, which is super interesting because this could mean that there is the possibility of actually detecting an interstellar object within the solar system from these nearby debris disks, and then therefore able to actually determine the host system from these objects. So the value itself, this is probably just an upper limit, but the fact that it is sort of not zero or taking hundreds, maybe thousands of years to detect these things is what the interesting thing is. And again, we can look at the flux of meteoroid sizes. So this time we use 200 microns because this is the most common size detected by radar systems. And again, we have this histogram, but I will point out just the actual value. We get the current flux at Earth for these sized objects being about 11,000 a year. So this is a very large number. And again, it's not the number itself that matters, but maybe it's not the fact that it's one every century that we could expect to see. There could be somewhat frequently. But 11,000 seems like a lot. What's the chances of actually observing these things? So if we look at CMOR, which is the Canadian Meteor Orbit Radar at Western in London, Ontario as well, its coverage is about 400 square kilometers, which is very small compared to the surface of the Earth. So that would mean at this number of 11,000 per year, it would take 80 years to be just 50% confident in observing one of these things. So even though this seems like a large number, it would take a long time to actually observe one of these things. CMOR has been orbit capable since 2002, so multi-station, being able to determine an actual orbit. So that would mean we're about 80% confident that we haven't seen one of these things from the radar yet or haven't been able to. Now, another size that might be interesting is sort of the larger sizes that can be detected by visual cameras for a meteor, because there is the Global Meteor Network, which is set up by a colleague of mine, Dennis Vida, at Western. It covers 17.5 million square kilometers of the sky, looking for meteors every night. Now, unlike the radar that detects meteors 24/7, this has to observe at night, and then you have to account for weather as well. So this time it would take 25 years to be 50% confident in detecting just one of a GMN sort of sized object, which could be about 3 or 4 per year. This has been in operation since 2018. Now the assumption that it's been this amount of coverage since then, it would still be only about 80% confident, or sorry, 80% confident that we just haven't observed one of these things yet. But the interesting thing again is that maybe they can. If we keep observing, maybe for 25 years, maybe we do see one of these interstellar meteors that are coming from one of these debris disks. Now, another thing I just want to point out here is, should interstellar meteors be obvious? So one of the arguments for why we haven't seen these things, and people sometimes say, well, shouldn't they be obvious? Like, shouldn't there be a subset of them where are very highly eccentric and therefore aren't on this heliocentric sort of boundary? Because right now, every time we sort of detect one that could be interstellar, the errors make it bound to the solar system. So why don't we see any that are sort of way out in the highly eccentric, that even if they have large errors, it's obviously interstellar? Looking at these debris disks and the material they deliver, we can look at their arrival velocities and their heliocentric speeds at the inner solar system and look at these eccentric values and see that the vast majority of them are actually very close to the parabolic limit. So this, I want to point out, is in a log histogram. So it's actually quite a few orders of magnitude difference from these very, very highly eccentric ones compared to the ones that aren't highly eccentric. So the median of which is around 2. So you would need sort of good measurements in order to determine whether or not these things are hyperbolic, rather than just seeing a vast majority of these which are highly eccentric when it doesn't matter sort of how bad the errors are. And I will end it there just to leave up the summary. it's just interesting to think that we could be seeing interstellar material from these nearby debris disks if we keep sort of observing. Vera Rubin's coming online in full operation soon. The number of interstellar objects that we know of will surely increase, and hopefully one of these things are able to be traced back to the origin system. We can really maximize the scientific return and really understand how interconnected the galaxy really is. Thank you.
Great. Thanks. We have plenty of time for questions. Renu and Mark there as well.
Thank you. Renu Malhotra, University of Arizona. This is very interesting, of course, especially in the coming years with LSST. I wanted to ask, you listed a number of nearby stars as sources. Did you consider the solar system itself as a source of interstellar objects? And one thing I can think of is one of the things that would be possibly distinguishable in terms of V infinity, because I think you showed simulations, or somebody did, about the ejection velocities from the solar system are low. The ejection velocities relative to the sun are on the order of a couple kilometers per second. So these objects would not drift terribly far, and when they do re-encounter the solar system, there would be gravitational focusing that would be more for these objects than for objects from neighboring stars. So we should, I think, expect our own ejected comets, objects, to be overabundant in what look like interstellar flux. So did you look at that?
No, we didn't look at actual sort of solar system material. This is super interesting though, because in some preliminary sort of simulations, we took the solar system, ejected material, and sort of saw how it progressed in the galactic potential. And we noticed that, at some point, although the orbit in the galaxy is enclosed, you do get this sort of stream closing in on itself that could sort of redeliver material to the solar system. So this would be very interesting. And I think I saw a term for this as a sort of quasi-interstellar, which I think is interesting. But I think that would be very interesting to sort of look at, and whether or not we can easily distinguish a sort of solar system, a past solar system object from something that's truly interstellar. Yes, yeah, and there are some that from these nearby debris disks that do have very, very small V infinity values, even from distant stars, and then some that are extremely sort of high relative velocity. So, and we did see sort of that gravitational focusing obviously does differ dramatically based off of that speed.
Good question from Jay.
Hi. I had a question. I thought this was really cool thinking about the solar neighborhood and what's coming our way. So in that same respect, there are more white dwarfs within 20 parsecs than there are G-type stars and A and F-type stars. So there's going to be, if there are Oort clouds or Oort cloud-like populations, there will be a significant fraction of things that become unbound after the mass loss of the giant branches. Have you considered what kind of population of interstellar objects might be created by such a population?
We have not done white dwarfs yet, which would be a very interesting sort of next step for this sort of dissertation, the thesis right now. We needed some sort of small sample set to do this with, but I would love for the next project to extend this to some very interesting other systems as well, and white dwarfs would definitely be among them.
Hello, this is Bryce Bolden from Eureka Scientific. So I think this is a pretty fabulous study. So you did a great job here, and it's very compelling results. So my question is, I know you talk about, yes, you're not likely to detect one of these objects in these meteors in a substantial, unless you have a substantial amount of time. But are you able to basically rule out certain properties of debris disks or putative debris disks around nearby stars based on the observations and comparison with the predictions from your model?
I think it would take more time to really constrain them, just based off of how long it would take to confidently see just one event. But presumably, if we were able to wait a certain amount of time, in 25 years or something like that, and we don't see any, maybe then we start to be able to constrain these other systems and sort of have an idea of how much material might actually be ejected compared to what these estimates are.
Great. All right, well, that's all the time we have. Let's thank our speaker again.